we go. Make sure that it is recording the voice too. Yes, it is. All right. Okay, so the homework assignment is this. Remember the homework assignment for this class? So there are any questions regarding the homework assignment? Yes?
This is like has more to do with the testing phase. Basically, like, is there a way to like, because I can't think of a way to like really load a register with a value to test it without like having to like re-hard code it. So like, I know about the restore command for memory, but is there a way to do
With
something
this
similar
one?
with registers?
Sure, absolutely. You can use the set var command in GDB to change the value of a register. Okay, so let me just kind of go ahead and start up the virtual machine, because I think I want to use the virtual machine for this class because everything is going to be consistent with your virtual machine, and it's just better that way. So we go to Windows, Linux, start.sh. There we go. So I'm just going to start up the virtual machine and tuck it away. But getting back to, so that's a good question. We'll address that today with some other stuff that we do. Other than how to test the program, are there any other questions, concept-wise, with this homework assignment, converting this subroutine into assembly language? Yep.
So when you're looking at that for X and Y, are we assuming that X and Y are on a global scale, or are you passing it as a reference, or are you passing it by value, or how?
Is that helping?
Well, yeah, but no.
So X is a global thing, Y is a global thing,
Okay.
and use register EAX as variable X, use use register EDX as variable Y.
Yeah,
So everywhere you see X, it is variable, it is register EAX. Everywhere you see Y, it is keep saying variable, register
No, I understand
EDX.
that part.
Yeah. So is that answering your question?
Yeah, I was just wondering if it's a global scale or not.
Well, registers are global.
Well, that's what was the question for the.
Yeah.
I didn't know.
Okay. Question?
Like one more thing about the ret in
The return?
assembly, yeah, the
Uh-huh.
return. I'm pretty sure the answer is going to be no anyway. But for how assembly likes to process instructions top down, like for the case of.
Okay, I keep overhearing the other conversation. So can you kind of hold it off until the end? Okay, go ahead.
For the case of the return, will it want to process the statements under that, or will it just jump back into wherever it was called from?
In the absence of return?
Well, in the case of return, like for example,
When you do return.
Yeah, when you do return, like will it want to run the instructions afterwards, or will it just pop back?
Let me answer that question. It's a good question, okay? And I will answer that question as well as your earlier question, which is how do you change the value of a register in one single swoop? Okay, so we'll see how that can be done. Okay, so let's start with this one. Okay, so I'm going to use the virtual machine to do this. So SSH-P2200 user-localhost. And this is just user. Okay, there we go. All right. So I'm going to run a particular program to illustrate both of those points. Okay. So let's go ahead and make a new folder. Okay. mkdir return. Okay, because it's just going to illustrate return. Return.s. Okay. So let's do the usual stuff, which is under .global _start. But at this point, it's going to be a little bit more fun. So we have L1 being here with a no-op instruction, L2 being here with a no-op instruction, L3 being here with a no-op instruction, and then we have finally L4 being here, and it has some instructions, which is the usual termination sequence, which is putting a 1 into EAX, putting a 0 into EDX, and then ask for a software interrupt. We'll get to these eventually, okay, but not at this point. So we have 4 label definitions, and then we have one single return here. Okay? So now what I want to do is to control where I go by using commands in GDB, so I can artificially push a value onto the stack, so it will be used and treated as a return address. So I can return, in GDB, using GDB commands, I want to be able to control, do I continue execution at L1, L2, L3, or L4? Does everybody understand what I want to do, what I want to accomplish? As it is, with this program, as it is, it's most likely going to crash. Because by the time I get to underscore start, what do I have on the stack? Is it a known return address that I put there? I don't know what is on the stack, okay? It may not even be a valid address to return to. So by blindly executing a return statement, it's not gonna do anything healthy, okay? So I need to do something artificially to put a return address on the stack so that when I single step the return instruction, it will get me to a particular place that I want to go to. Is that okay? All right. So it's going to illustrate it's going to answer both of your questions, because the first one is, how do I mess around with a stack pointer and stuff like that? Because that's what I need to do to emulate the call of a particular subroutine. Okay. So let's do that. Link it, GDB. Okay, so we put a breakpoint at the very beginning of this program, run the program, and the first thing I want to do is to say, okay, where is the stack pointer pointing to? The stack pointer is pointing to BFFFF7B0. Okay, so I'm just curious, okay? You don't have to do this, but I'm just curious what is on the stack at this point. Because the operating system put something over there, I just don't know what it is. So I'm just curious, show me what it is. So use the X command. I want to look at one thing as a word which is 33 wide in hexadecimal, and it is located exactly where the stack pointer is. So this is the first trick that you need to kind of remember, or just kind of make a note of, is all the registers are available as quote-unquote variables in GDB if you put a $sign in front of it. Okay? And that includes AL, AH, AX, and so on and so forth. If you just put a $sign in front of it, you can quote-unquote use it as a variable. Okay, so I'm just curious. Find out what it is. That doesn't look like a very healthy location to go back to, but I'm going to single step the return instruction just to see it crash. Okay? Which doesn't sound like a very productive kind of thing to do, but it is. Why do you think it is productive? Knowing a program is going to crash, intentionally saying, yes, let's crash it and see what happens.
To make sure it does.
Okay, to make sure it does, okay? But what is the other reason why we might want to do that?
So that when you see the same error code, you know why.
Exactly. Okay, so if we know that when you have a wrong return address on the stack, knowing the return address is one which is a bad place to go to continue execution, and I still ask the program to go like, yeah, let's go ahead and return as if it is okay. We want to see the error message. So single step, it gives us this kind of really odd message, but it is not really that odd. It's basically saying, I cannot execute at location 1. That's what it's saying. Okay? It doesn't seem like it's even a crash. If I single step one more time, then it says, cannot find. Okay. So this is the symptom. It doesn't give you a segmentation fault, but instead, it will basically give you that one message here that is indicative of a problem of this nature. So next time you see something like this, then you know that whatever is on the stack right now really should not be used as a return address. Now, why is it not a good return address? There can be multiple reasons. One, the stack pointer itself is pointed at the wrong place. Two, you overwrote that location with something else. So there can be multiple reasons why your program might do something like this, but at least you know that you are returning to the wrong place when you see something like that, okay? Which can come in handy not only with this homework assignment, but with pretty much all the future homework assignments. Okay, so knowing that this program is crashing the way it is, we are going to restart the whole thing. Now we're back to the return instruction. So this time, I want to push something on the stack, okay? I want to push a valid return address on the stack so that the program will continue execution at that place. So now the question is, how do we do that? The first thing we need to do when you push something on the stack is what? Remember the few instructions to push something on the stack. What is the first thing that you do? Yep.
You gotta increase stack pointer by 4 bytes.
By 4? Yeah, not by 4 bytes, just by 4. Because the processor is byte addressable, so when you subtract 4, you're moving by 4 locations, 4 byte locations. But I know what you meant. I just want to kind of clarify that you cannot subtract 4 bytes. You're just subtracting 4 as a quantity from the stack point. Okay? So this is where I will answer your first question. How do you set the value of a register? There's a command called setVar, or set variable, which can be used to set any variable in C and C++. But in assembly language programming, we don't exactly have variables. We have registers, but it also works on registers. So you basically say, I want ESP to become ESP -4. Is that okay? This is also what you would have done in just regular C++ code. Okay? I believe, but I'm just curious whether this will work or not. I believe so. Okay? You can also do a minus equal to, which is called a compound assignment operator in C and C++. Okay, let's try that out. Seems to work. So now that we have allocated 4 bytes on the stack, because anything that is above where the stack pointer points to, or at or above, is now quote-unquote protected, I can now copy the address of L1, L2, L3, or L4 over here. Is that okay? So to do that, we can use setVar to do that, because we can basically say setVar, and ultimately we want to use a dereference. Okay? But what we are dereferencing, or what is inside the parentheses, has to be a pointer of 4 bytes. Okay, so I'm going to force it to become a 4-byte thing, and because this is a 32-bit architecture, integer is 4 byte. So I'm casting ESP as a register as if it is a pointer to a 32-bit integer. So this way I know it's going to overwrite 4 bytes at a time. Is that okay? And then the next thing I need to do is to say, okay, but what goes into these 4 bytes? What do you think I should go in? Which label do you want to go to? L1 is kind of not fun because it's right after this. Do you want to skip to L2 or L3? L4? Okay, let's skip to L4. Okay, so we'll say L4. Press the Enter key. Okay. Well, let's check whether it makes sense or not. Okay, let's check what is in ESP. So IRESP, or that won't work because we want to see what is at the location that ESP points to, which goes back to the earlier instruction, which is this one, which is showing you what is the 32-bit at the location where the stack pointer points to. It looks like this. Okay. You look at this number and go like, well, I'm not really quite sure this is a place where we can continue execution. Maybe I can look at my current point of execution so that we have a rough idea of, well, at least is it in the right neighborhood, okay? And that is what EIP is. EIP is the instruction pointer, which is also known as the program counter. That is the location where the return instruction is located. So when we press the Enter key, we see, oh, okay, they're off by 4 bytes. Does that make sense? Each no-op instruction is exactly 1 byte. So do we have 4 bytes or 4 no-op instructions between the return instruction and label L4? Yeah, we do. Yeah, so it makes sense to me, okay? So now that we have set up the stack, the whole thing, we can now say, well, let's go ahead and single step and see what happens. Single step, now we are on line 16. Well, is line 16, is that really label L4? From what you see here in GDB, can someone confirm that, yes, we are at label L4? Just look 2 lines before the GDB prompt. What does it say? L4, open and close paren.
And then the next line number is 16, so.
Yep, it knows the line number is 16. It also knows that this location is also known as L4 as a symbolic name. So now we have multiple confirmation that yes, we end up at the right place. So is that answering both of your questions in a kind of tricky way?
Also like what happens like after the return statement is processed? I also want to. Can we step through one more time and see like?
Absolutely. We'll go through this one more time, and this time I'll do something slightly different from the previous
just
time.
the next step to see where I want to jump back to.
Okay, sure, absolutely. Okay, so we are back to the beginning of this program. Everything is now reset back to the original state. So the first thing we want to do is to say, well, tell me what is in ESP. Now there are several ways to look at the content of ESP. You can say print ESP, which is going to be in decimal. Oh, I guess not, because it knows it's a pointer. So this is one way to do it. IRESP is the other way to do it. So there are usually multiple ways of doing the same thing. So we kind of take note that before the return instruction, it is at this location. But remember, this location has something that is important, but it's not our return address. So we need to plant a return address on the stack first. And do you guys remember how I did it the first time? Because that code is still here. Okay. The question is, can I do it in one single step instead of 2? Okay. So what I'm asking is, looking at these 2 GDB commands, the question is, can I combine these 2 into one single command? Sorry? The question mark? You mean the ternary operator? Okay. Okay, so do we do a pre-decrement or a post-decrement? If you look at the sequence here, we are doing the subtraction first, so it's a pre-decrement. Okay, very good. So I will combine both of those into one, and this time we'll go to label L3 instead. So we say set var, okay, using a dereference on this side, and then the other side is just L3, okay, no big deal, that part is easy. This part here still requires a cast because I want to make sure that I overwrite 32-bit, instead of 8 or 16-bit. This time inside here, what I'm casting is going to be ESP minus 4, minus equal 4, which is a compound assignment operation. But the result of the compound assignment operator is going to be the new value of ESP. So I'm combining the 2 steps that I have highlighted at the top part of the screen into one single command over here. Yep.
Why can't we use move L?
Move L?
Yeah.
Because if move L is not a part of the program already, I cannot execute instructions ad hoc. In the absence of a better word to describe it, there's no ad hoc assembly instruction that I can execute. But if it can be expressed in C expressions, GDB understands that instruction in what I'm typing here. So it's GDB actually doing it. It's not the program itself doing it. Okay. Any other questions? So I'm hoping this is not surprising anyone because I'm just really using regular C, C++ notations here. Okay. So press the Enter key. The first thing we'll check is, okay, but what is ESP at this point? So we say print ESP. What are we expecting ESP to be? It used to be BFFF F7B0. This should decrease by 4. Which means it should end with A, no. What is 16 minus 4
Oh, 12.
is 12. What is the hexadecimal digit representing 12? C. C.
10 is A. Oh, yeah.
Yeah. Okay. So we're expecting the new value of ESP to be BFFF F7AC. Okay. So let's see whether that is the case or not, and that's exactly what we have. Which is good, okay? Because when I do something like this, I want to predict what the program is going to show me, and then I run the actual command to confirm that that is correct. Because if I have any type of misunderstanding, then it's going to show me that, oops, I made a mistake. Okay, at least one of my assumptions is incorrect. Okay, so this is all good. Then we single step the return instruction. We get to L3 because the way I confirmed we are at label L3 is because of L3 over here. But at the same time, we also want to know what is in ESP. What do you think ESP, or what do you think is the value of ESP at this point?
It will be 1.
Hmm?
1. That 0, 0, 0, 0, 1.
No. No, we are looking at the register, not what it points to.
Oh, okay.
If the return is finished, then would we?
The return is done already.
Then would we expect to be back to B0?
Exactly, because when you do a return, there's an implicit pop in the return, which means we are consuming a particular value on the stack and move the stack pointer so that that value is no longer what the stack pointer is pointing to. So B0 is a good expectation, but we need to confirm that, and that turns out to be true. So this is all good. Sorry?
It's like magic.
Well, not if once you understand the mechanism, it's no longer magical. Yep.
So my other question was as a program progresses, is it going to want to run those other 3 no-op instructions, or do the
Yes, it will fall through. So we are at L3 right now, right? So if we single step this L3, which only has a no-op instruction, it moves on to L4, which is where the move L instruction is located. In other words, in the absence of RET or the return instruction, there's no actual boundary at where you define the end of a function. So that means it is exceptionally important for you guys to remember to put a RET instruction, the return instruction, at the very end of a subroutine when you write it in C, when you write it in assembly language. In C or C++, okay, you need curly braces to define the body of a subroutine. If you miss the end curly brace, it's a syntax error. The compiler is going to chew you up, right? It'll give you lines upon lines upon lines of error messages. The first one is the one that is important, but you won't miss it. But in assembly language programming, if you have a subroutine definition and you forget to put an RET instruction at the very end, the assembler is going to go okay, fine, we'll just kind of continue with whatever code is after that. Sometimes you know what it is, sometimes you don't. So that's why it is important to remember the return instruction when you define a subroutine in assembly language. Are there any questions about the return instruction or the stack pointer, or how I emulate the effect of calling by an expression in C that looks like this? Yep.
We didn't have the call and return, but we just used the move instruction and subtract.
Correct. If we do not have the call and return as instructions, you can use the move, subtract, and the add instruction. But the return is a little bit tricky because the return requires a particular jump instruction that we haven't talked about before. We did talk about it last time, but we don't usually use that, which is jump, asterisk, and then a particular register that contains the address that you want to continue execution at. So that's the only part that is kind of tricky, is you have to use up one register. All right. Any other questions? No other questions regarding the call or the return instruction? Alrighty. All right, so if there are no questions about the call and return instruction, we are going to move on and talk about other things that are also on the stack. Particularly, we'll move on to local variables and return values. I may not have, oh, okay, they're all fixed. Okay, call frame. I'm just trying to sequence my material here. I think we'll take a very short break from assembly language programming, and we'll go ahead and trace a program written in C, C++, and we'll take a look at a really cool feature in GDB called frame. Okay? Because that is going to show you how things are kind of organized. Even though you don't know exactly how it is organized on the stack, it kind of gives you an idea of, oh, okay, I can see several things happening on the stack. All right, so that's exactly what we'll do. Get out of this one, and we'll just write a program doing factorial. So here's the factorial program, and well, it can be unsigned, because we know that factorial doesn't deal with negative numbers. So it's unsigned factorial, unsigned n as the parameter. And I'm going to do it the long way because I need a place to stop for each call. Okay, if I do it the short way, I may not have convenient places to stop. So I'll do it the long way, which is using a conditional statement, because I can do the whole thing with a return statement with a ternary operator. But in doing that may present a certain problem because I may not have a place to stop. So I'll do it the long way, which is while if n is less than 1, less than or equal to 1 works too. So less than or equal to 1. Then we want to, okay, this is philosophically, I really should do this. Okay, I have a result here. So when n is less than or equal to 1, result is going to be 1. Otherwise, result is going to be something else, and then return result here. So result is 1, because the factorial of 1, 0 are both 1s. And then if n is greater than 1, then the result is n times the factorial of n minus 1. Okay, so this is a fairly spelled out recursive way of doing factorial. Are there any questions about this program itself, or this subroutine function? No questions? Okay, so everybody feels comfortable with recursion? Is that okay? All right, okay. So we'll just go ahead and have a main here, and now I don't know whether this will work or not, okay, because it depends on how smart the compiler is. I'm just going to say the factorial of 4 without storing the value. In other words, I'm computing the factorial of 4, but I'm not doing a single thing about it. A really smart compiler will optimize this entire thing out and end up doing nothing. But if the compiler is just compiling the code and assume that there's something important with factorial, then it will still give me the function call. So I don't know whether the C compiler or GCC is smart enough to optimize everything out. We'll give it a try. So we have gcc-o fact, which is the name of the executable, fact.c, which is the source code, and compile the whole thing. Okay, this is bad because I'm not doing what I preach. Okay, in my C++ class, cisp310, I always tell people to do a dash wall, which has nothing to do with Donald Trump. What do you think wall stands for?
It's a level of.
And by the way, he's not original either. The Chinese built the Great Wall several thousands of years ago, so he just copied. Yeah. Okay, so what is this dash wall? It's warn all. Okay, it will give you everything that's possible as a warning message. Okay, so it will spot potential issues. The other one is pedantic, which makes sure that we are not using any features that are specific to GCC, Because GCC has certain extensions that you can do certain things in GCC, but it won't work in other C compilers, even though they are also NCC compliant. So pedantic, make sure that you're not using those features. It will give you messages if you try to use anything that is specific to GCC. Okay? So press the enter key, and no warnings whatsoever. That's good. So now we can go ahead and run the program. Nothing happens as expected, okay? Because the program doesn't print anything, it doesn't have anything that is visible from the outside. If we GDB, maybe we can do a little better. So the first thing we'll do is to put a breakpoint at the function. At the very first part of the function, we want to put a breakpoint to stop. So you can say bfact, which is the label name. This works, okay? And then you can just run the program. This is the first breakpoint. Now here, I want to show you something that normally is not doable in assembly language. It doesn't make sense. But in C and C++, you can do it. It's called BT or backtrace. Now backtrace, it doesn't give me the parameters. That is not what I expected to do. Help BT, maybe it has a road to do it. Okay, BT full, there we go. BT full. There we go, no symbol table. Oh, that's why. Okay, because I forgot to compile with debug option. So we add a -G to this one. Now we can have debug information. So the -G with GCC is kind of the same thing as -G steps with the assembler. Okay, accomplishes exactly the same thing. Okay, so now we run it again, much better. We have the source code and all kinds of stuff like that. So when you say BT, BT one word, it shows us that we came from main. The call of factorial from main happens on line 19. We are now in factorial with a parameter of n equals 4 on line 4 of the entire program. Okay, well, you kind of know that this is no big deal, right? But because this subroutine is recursive, let's check out what happens next. So I'll do a continue. Well, if you want to, we can single step. So we can single step. We are now into the else of the conditional statement, which is by itself recursive. So we are now calling factorial on line 10 to factorial itself. Continue, and we're now back to line 4. Okay, so now the big question is, oh, so this means we just called factorial from inside factorial. Okay, how does that work? What about n? N used to be 4, now it is 3. What about the one that used to be 4? Is it still somewhere out there, or is it gone completely? It's still there, okay? But how do we see that? BT, okay? Backtrace. So with backtrace, it is showing us that with the current place that we are at, is on line 4, with parameter n being 3. How did we get here? We got here from line 10, which is also in factorial itself, but in that particular invocation, n as a parameter had a value of 4. It is still there, okay? We still know the old n, it's just that we cannot access it at this point, because we are now in a different invocation of the same subroutine. Is that okay? So we can continue with this one. If I continue several times, 2, 1, okay, single. So this is the last one because we are not going to do another recursion at this point. So when we do a BT, we can now see every single invocation that is still active, just, you know, it's still there, it is just not the current invocation. Are there any questions about what we see here in GDB? It is showing us how we got here.
Like all values that you.
These are all the previous invocations of the same function. Yep.
Like, are the, like so as this goes along, are these like instructions or values being stored in memory somewhere, or is it?
Exactly. In order to see that we have quote unquote 4 n's, each one has to be stored somewhere in memory, because otherwise there's no way to track these different 4 ands, the 4 different parameters. Is that okay so far? Okay? So one thing we have to remember, if you're not comfortable with recursion, this is what you need to remember and adjust, how you think about things. Local variables are not on a per function basis, they are on a per invocation basis. Let me just say that one more time, because I personally think this is important. When we think about local variables and parameters and return addresses and stuff like that, they are really not on a per function basis. It is on a per invocation basis. What is the difference? Does someone want to explain the difference between an invocation of a subroutine versus the subroutine itself? Go ahead. Give it a try.
When you say invocation, that means that at the time of the function being called, that local variable exists.
Whereas soon.
Oh, you don't want that? Too loud.
Too much power.
So when it gets called, that it exists, but when it's done calling, when it returns, then that variable is gone on the invocation basis.
Right. So what starts an invocation?
A call.
A call. Very good. Okay. So the function is already there. The function is nothing more than instructions on a piece of paper, but nobody is following the instruction until you have an invocation or a call. When does an invocation end? When you get to the end of the subroutine, when it hits a return. It can be explicit, like a return statement, or it can be implicit when you hit the end curly brace of the definition of a function. Very good, okay? So an invocation starts with a call, it ends at the very end when we execute all the way to the end of a subroutine. When you have a case of recursion, then you can have multiple invocations of the same subroutine, quote unquote, stacking up. Right? Because every single call of the subroutine starts a new invocation. But remember, local variables, parameters, and return addresses are on a per invocation basis. That's why we see what we see here in backtrace. That's why we have 4 ands, because each one corresponds to one invocation of the subroutine. Is that okay? Is that helping to clear up some of the concepts of recursion? Or not? Tag, you're making it worse. My head hurts. Okay, but that's how it works. Okay, so we have 4 invocations, and we are at the last one at this point. Now, it's not going to be helpful in this case, but in debugging a C or C++ program, it might be helpful. Okay, because if you want to check out, and say that we only have 1 parameter per invocation, which is easy to track because it's already printed here. But if you have local variables, it doesn't get printed here, okay? So what you do is you do a BT full. Then when we do have local variables, it will show the we have result as a local variable. So it is showing all the local variables. So this can be helpful when you're in CISP, let's say 430, when you have to write a recursive subroutine to deal with a tree structure of some kind. This is going to be helpful because it will show you, all the local variables along each invocation in a recursive subroutine. Is that okay or not? Concept-wise. Okay, all right. So we can actually tell that not only do we have 4 parameter ands, we have 4 results, and they're all different. Is that okay? What do you think about the addresses of these ands and of all these results? Let's see if we can find out a pattern here, okay? In other words, I want to know what is the address of this end compared to the address of this end compared to the address of this end. Because once we figure out the addresses of 3 ends, we can probably start to see a pattern. Like there's a certain difference between the addresses of those ends. Is that making any sense? Okay, so we'll start with the first one. The first one being the one that we are currently at, which is this n. And that's an easy one. Just print the address of n, it gives us the address. What about the other one? What about the one at number 1? In other words, what about the one at the previous invocation? What about this n here? How do we know the address of that n? Well, what we need to do is to change our frame, okay? So the next command is going to be important as well. It's called frame, and you can supply a number to frame to basically follow the number here. If you just say frame, the implicit parameter is 0. It goes back to the top level one. But if you supply a number, you can go to any frame that you want. So in this case, I say frame 1, which will basically put me into this particular frame, which means if I ask for the address of n, it's going to give me the address of this n and not the n at the top. So I will do a frame 1, and this is where we are at in that particular invocation. I do a print $n, and it is 6A0 as opposed to 70. Okay, so now we are starting to see something that may not be really surprising. The latest one, the last n that we looked at, ends with the address of 70 in hexadecimal. The one prior to this one ends with A0. So not even calculating the actual difference, we already noticed one thing. It's decreasing. Okay? With additional invocations, the address of our local variables or parameters in this case is going to have a smaller address, which is consistent with something that we have done so far with stacks. As we push items, the new items always grow lower. Okay, so this seems to have something to do with a stack. Let's do it one more time. Okay, so we go to frame 2 in this case. Frame 2, print the address of n, and this time it is a D0, okay, yet larger. Okay, so the more we track back in time, the earlier the frame, the higher the address, which is consistent with the operation of pushing. Now, let's look at the differences. Okay, what is the difference between a D and an A? It's 3. So D0 and A0, they're off by 48 bytes. What about between A and 7? It's also 3. So we are also off by 48 bytes. So that means, hey, there's something regular going on here. Okay, every time we call the subroutine, it seems like it will consume another 48 bytes. And of those 48 bytes, n is on it. And guess what? Result is on it as well. Are we still doing okay so far with this observation? Can someone kind of guesstimate where about is the stack pointer pointing at this point? Just give me a neighborhood. It doesn't have to be exact. Sorry? -4? No. I'm talking about the stack pointer itself. In other words, if I were to say print $ESP, what kind of hexadecimal number should I be getting at this point? It will be an address, okay, but what range? Give me an estimate. Based on what you see here on the projector, just give me a guesstimate of what the stack pointer should be pointing at this point.
Probably within 16 bytes. Probably within 16 bytes.
16 bytes.
Less than that address? Or
Less than which one?
the one we're currently on?
But that's an earlier frame. We are actually on the first frame. So in other words, the latest n has an address of BFFF670. So where do you think the stack pointer is located at this point? Well, okay, go ahead, sorry.
Around there.
Around there. Is it going to be lower or is it going to be higher? It's going to be lower, okay? It's going to be lower because anything below where the stack pointer points to is unallocated. So in order for us to have local variables and parameters and stuff like that, they have to be on the other side of the stack pointer, which means the stack pointer has to be lower than or equal to BFFF670. Is that making any sense? Okay. And I'm just guessing it is 650. Okay, so I just randomly choose an offset. So let's check it out. So print $ESP. It's 680, which is this number here. Doesn't make any sense. I think that's because I have changed the frame already. Let's go back to the original frame. So we go to frame, which automatically goes to frame. Oh, no, I take it back. I lied. You have to say frame 0 to go back to the original frame. There we go. So I want to look at ESP again. It is 640. I'm off by 16 bytes, but close. Okay. Through all this observation, where are the local variables and the parameters? Just some random place in memory, or do we have a name for that chunk of memory? They're all on the stack. Very good. Okay, so they're all on the stack. So the stack is extremely useful in C and C++ programming because we are not only going to store the return address on the stack, but we are also storing all the local variables and all the parameters on the stack. Is that okay? I mean, is this helping to illustrate the idea that everything that is local, including all the parameters, are on the stack? Yep.
So like that's within like the 48 or so bytes between each of those
Yep.
increments, like all those are going to be like the.
And each big chunk is called a frame. And each frame is created for each invocation of a subroutine. So every invocation will create a new frame on the stack. In the frame, we store all the local variables, we store all the parameters, we store the return address, and a few other things in double quotes on the stack. But collectively, it is called a frame. Is that okay? Is that concept okay? Yep. Oh, I thought there's a question. Okay. If there are no questions, I am going to, I'll go ahead and do something to illustrate, how to interact, how C code and assembly code can interact. Okay, and by doing that, it will also illustrate how things are arranged on the stack. So that's what I'm going to do next. But I will start with something that you already know. We'll start with a swap subroutine. So this is a void function called a swap. Okay. So with swap in C, which does not have passing by reference, we have to pass a pointer. So this is a pointer to an integer x. This is a pointer to an integer y. And in the subroutine, we have a local variable t, so that we can do the swapping. So t gets whatever p points to, whatever p points to, px points to, gets whatever py points to, whatever py points to, gets t. That's a fairly typical way of doing exchange or swap in C and C++. And in the main function, I have two local variables. I is initialized to 16, and j is initialized to -7. And then I just call it a subroutine swap. Okay, the address of I, the address of j, and a single return statement after that. Are there any questions about this program in C and C++ form? Is that okay? All right. Do you think it's going to work? Yeah, I'm pretty sure it's going to work, but we'll test it first. So let's go ahead and test this program. GCC-1 pedantic-g-o that GDB swap. We'll put a breakpoint on line 14 and another one on line 15. So we can run the program. We know that I and j have specific values at this point. Continue execution. When it comes back, we look at I again and j again, and their values are now exchanged. So nothing really surprising, the code does work, but it just does a really kind of simple thing of exchanging the values of what the pointers point to. Is that okay? Are there any questions about this code here? No questions? Okay. So now I want to implement the swap subroutine in assembly language, and yet retain the call itself from main in C. Yep.
I have a question.
Yep, go ahead.
Why does GDB, like, whenever you print something, it assigns it to like $?
Because you can refer to that value using that dollar. In other words, in this case, if I want to calculate what is -7 plus 16, I can do something like this. What is the result of the third command and the result of the fourth command? So is that answering your question?
Yeah.
It's kind of a neat feature too, because you can refer to the result of an earlier query without having to repeat the entire thing. Any other questions? Okay, so we are going to implement swap, but this time in assembly language. So before we do that, I just want to go back to the notes here and just kind of explain where we are at in terms of the notes. We are now at parameters, local variables, and return value. And also C calling convention, that's also going to be a useful one. So this is actually Wikipedia, but it applies in this particular class really, really useful. So we'll keep an eye on that one. All right. And this is basically where we are at. Okay, the note is not done yet. And that one is not either. Oh. Okay, I have to make sure that I unlock those first after the class. Okay, but getting back to this, oops, not this one, where am I? Yes, you're here. Okay. So let's take a look at the C code first. And, well, in fact, we'll do a V split, vertical split, so that we can now use the other one to look at the assembly code of swap. So we'll edit swap.s, which is the assembly version of that. Okay. The first part is easy, okay? Swap has an entry point with a symbolic name of swap and a return instruction at the very end. So these two, they have to be there. Swap as a label definition is defining the entry point of the subroutine and has the same name as the C subroutine. Return has to be here because by the time we're done with the swap operation, it has to get back to where we call the subroutine. So return has to be here as well. Okay. So now the first question is, what about the parameters? Where are the parameters by the time we get into the subroutine? We know they're on the stack, but who is responsible of putting the parameters on the stack? I'll give you two choices, the caller or the callee. The subroutine being called or whoever is calling the subroutine. Who is responsible for putting the parameters on the stack? The caller, okay? It has to be the caller because main is the one that specifies the address of I and the address of J. So main is the caller on the line of the swap call. Okay, that's good. So the second question is, we already know the parameters are on the stack. So the next question is, where are they on the stack relative to the return address? So now you have to think about the ordering of the events. Do we call swap first and then we push the address of I and the address of J? Or do we push the address of I and the address of J before we call the subroutine? Push and then call. Very good, because by the time we call, it will continue execution in the subroutine. The caller has no control at that point anymore. So they have to be pushed first. Okay? All right. So we know that there are 3 items on the stack at this point by the time we get to swap as a subroutine. We have the address of I, the address of J, and the return address by the time we get to the entry point of the swap subroutine. In what order?
Like
much return address was put in latest.
Okay, that's good. Okay, return address is put in the latest, which means it has the address that is the highest or the lowest? The lowest, very good. So we know return is down here, okay, at the lowest point. And the other two has to be higher. So the next question is, okay, what about the address of I versus the address of J? Which one has a higher address? That one is kind of tricky because I can see people saying, okay, you know, the second parameter is the first one that we push, or we can see people saying the second parameter is the first one, the last one that we push, okay? The actual order is last parameter pushed first, which means it has a higher address. There's a reason for that. I'm not going to get into it at this point, okay? But we know by the time we get to the label swap, even without any instruction in swap, this is what we expect on the stack, with the stack pointer pointing to the return address, because we are right after the call instruction. Yep.
So the parameters are kind of pushed onto the stack in reverse order?
Yes, they're pushed in the reverse order. The reason has to do with in C, you can have functions that have a variable number of parameters. That's the reason. Okay, but the convention is like that. The last parameter is pushed first. Okay. All right. So if I just do nothing at this point, can we confirm that this really is the case before we specify any code in swap in assembly? Can we use GDB for this purpose? Let's do that first. So I'm not even so worried about the implementation of the subroutine. I just want to see these things on the stack first and see if we can confirm all of this using GDB. Okay? But we have two problems. The first one is until I do a .global swap, the swap label is going to be local to this file and the linker will never see it. So we need to have a .global in order to tell the linker and say, hey, this label swap is actually important to the linker, export it. Okay, make sure everybody can see the label swap. The second problem is in the C code, we still have the swap subroutine definition. So we are going to change this by using a prototype here. And this is a nifty trick of commenting code in C++ or C++ is to use conditional compilation. Do you guys know about conditional compilation?
Yep.
No? Yes? Sort of? Okay. So this is a pre-processor feature. Pound if has a matching pound and if. The condition after the pound if can either be true, which is non-zero, or false, which is 0. If it is false, then whatever is between the pound if and the pound and if is as if it is not there. So this is how I can just comment out a block of code with just one line saying pound if 0 and the other line saying pound and if. But I can do the same thing using slash asterisk and asterisk slash. You know, the beginning of a comment and the end of a comment. There's one problem with the comment approach. It cannot nest. This can nest because it's done by the C preprocessor and it can nest. So it's a nifty little feature to do something like this. All right, so we have the C code, we have the assembly code, and now we want to combine the two. I'm not going to get into makefiles today because that's going to be a distraction. So we'll just go ahead and use GCC for both. So we have one all, we have -G to include the debug information, -pendentic. Then we have -O to specify the output of the executable. Then we specify the source code. One is swap.c, the other one is swap.s, just like that. Isn't that cool? The C compiler actually knows how to assemble assembly language code. It's by the extension. So when GCC encounters the source code with an extension of .s, it knows it is an assembly source file, and it will translate that accordingly, which is a kind of nifty feature. So now we have a program, an executable swap, that is partly done in C and partly done in assembly language. So the question is, well, is that really going to work? So let's do a GDB swap and put let's go to main. So do a list Here's main, put a breakpoint on line 17 because we want to see what happens when we execute line 17. Run the program, we are now on line 17. We're going to do the usual thing just to make sure that I has a value of 16 and J has a value of -7. Everything is as expected, no big deal. But we also want to know the address of I and the address of J, because otherwise there's no way for me to make sure that the content is on the stack in the right order. Okay, so we need to know the addresses of those two. Now we do a single step. And when we single step, you can also see that we were in the C file before. Now we are in the assembly source code. We're on line 3 of swap.lowercase(s), which is written in assembly. Well, we're at the return instruction already because I don't have any code in this subroutine just yet, because the point at this point is just to see what is on the stack. Okay, so let's check out what is the stack pointer at this point. So we say print ESP. This is the stack pointer itself. It is pointing to location BFFF6EC. Okay, the theory is we are now pointing to exactly the return address. On top of that, we should find the address of I. On top of that, we should find the address of J. One particular command comes in really handy, which is the X command. X stands for examine. Okay? It allows you to examine memory. So X/3 items. Each item is a word which is 32-bit wide in GDB, in hexadecimal. And we are going to examine exactly where the stack pointer is pointing to. Press the enter key, we got 3 values. Is that looking reasonable to you? In other words, the first thing that it points to, does it look like a return address? Does it look like a place where we do execution and stuff like that? Just the range, does it look like the right range to you? The 08048419. Well, in order to make that determination, let's check out the address of main, because it should be around there, because this is just part of the main subroutine. So we can say print the address of main, and that is 080483EC. So we just look at the last 3 digits. 419 versus 3EC. I consider that close enough. Okay, so it looks reasonably good for a return address into some location you made. So I would just let it pass. What about the BFFF70C? Don't we see that earlier in $3? What is that? It's the address of I, okay? And then the other one that ends with 708 is the address of J. So we kind of know that, oh, okay, so the suspicion was right, okay? This is exactly how things are organized. Because the caller really doesn't have a choice but to push the parameters first and then do the call. It cannot work the other way around. Now, within the 2 parameters, the reason why we push the last parameter first is because in C, you can define subroutines that have a variable number of parameters. So it's necessary for that feature to work that we push the last parameter first. Are we still doing okay so far with all this stuff here? Is it okay or not? Okay. All right. So now that we have a confirmation of how the caller is arranging these things, can we implement the function itself? Given the next 15 minutes, can we actually implement the swap subroutine? That's the next question. So let's get out of the GDB and we'll take a look at both programs. We'll take a look at swap.c, which is the C code, and swap.s, which is the assembly code, side by side. In other words, we want to implement this stuff here, or the equivalence of that stuff, over here right before the RET instruction. Okay. Well, the first thing is, have we introduced sufficient instructions and concepts to get this done now that we know the stack pointer is pointing to this location? That's the first thing. What do you guys think? I think we've got enough, okay? Even though it can be a little bit cumbersome, It can be done. Okay. So we take a look at the whole thing. There are nifty little tricks we can do in assembly that we cannot do in C to do the exchange stuff. Okay. So we are going to say what we really need is to put the pointers, which is PX and PY, into registers. Because once those addresses are in a register, then we can use indirect addressing mode to modify what they point to. Is that okay? Is that making any sense? Or not? Okay. So, to comment, I want to say, okay, the first one is, now remember, there are certain registers that you can destroy and use in the subroutine and other ones you cannot. EAX and EDX are guaranteed to be okay to destroy. Okay, so you're free to use EAX and EDX any way you want to. So we want EAX to be PX, we want EDX to be PY, so we can do little tricks, okay? So now the question is, how do I put this item on the stack, the address of I, into EAX? How do we get the address of J into EDX? We already know the distance to those particular items from where the stack pointer points to. Okay? So we want to figure out, do we have the necessary instructions to do all of this stuff here? Yep.
Can you do exclusive OR?
We cannot, well, there is the exclusive OR instruction. You mean to use it to do the swap?
That only works in C?
That will work in C, but in assembly, it's not going to save you much time.
Okay.
But at this point, I just want to get PX as a parameter into EAX and PY as a parameter into EDX. We'll do one at a time, focus on one, okay? All right, so the first thing I want to do is to say, okay, let's copy the stack pointer itself into EAX. So this part you might want to draw and add to your notes. So what we are doing is we are saying EAX is now also pointing to the same place where the stack pointer is pointing to. Is that okay? If you copy the stack pointer, you make another thing point to the same location. So we have two things pointing to the return address at this point. Is that okay? Sort of? Maybe? Okay. Next thing I want to do is to say, but I am not interested in the return address itself. I'm interested in PX, okay, which is the thing right after the return address. Okay, we can do something like this, right? We can add 4 to EAX. So by adding 4 to EAX, then EAX is no longer pointing to the return address. Instead, it is now pointing to the address of I. Yeah, I just added 4 to it. Because they're 4 bytes apart. Is that okay? All right. But I'm not interested in the address of the parameter. I want the parameter itself. So how do I get the value of where EAX is pointing to into EAX itself? What about this? Would that work? I'm just, the first part, which is the first parameter or the first operand, is saying, okay, let's take a look at where EAX is pointing to, grab 4 bytes at those locations. Okay, here are the 4 bytes that we just got from memory where EAX points to. What do you want to do with this? Let's go ahead and use those 4 bytes and override EAX as a register itself. That's what the second operand is specifying. So after this, okay, EAX is no longer pointing to this location. Instead, it is pointing to something earlier on the stack, which is down here. Is that okay? So with these 3 instructions, I have just put the parameter PX into EAX, register EAX. Are we doing okay so far with this part here? So if you want to write down notes, you want to kind of copy the picture, this is really important. And then the instruction over there that's being recorded, you just have to say, okay, you know, that part is recorded. You don't have to write down the exact instructions. But is the concept okay? What about EDX? I want EDX to be the address of J, which is also known as parameter PY. But it's going to be very similar in terms of the instructions, so I'm going to do a copy and paste, except we are dealing with EDX and not EAX, so I'm going to change all the EDX. I said EDX earlier. EDX, by the way, is one of those registers where a subroutine is not supposed to modify. Okay, if you are modifying EDX, you better save and restore it, so that to the caller, it is as if it has not changed. Okay, so we're almost done, but this is one problem with copy and paste because I forgot to modify one thing. Because at this point, EDX is also going to be the address of I, because that's 4 bytes away from where the stack pointer points to. What do I need to change to make it the address of J? 8 instead of 4. Very good. Okay, so we change this 8 to, change the 4 to an 8. So that now,
EAX in the move outline.
again, oh, I forgot one more. Yep, thank you. There we go. All right. So now we have EAX being PX, we have EDX being PY, and I want to exchange the values that these two registers point to. I can emulate the whole thing using another register. I think EDX is free to use as well. So you can use ECX, excuse me, we can use ECX as the local variable T. But since we have push and pop, we have another nifty trick to do the same thing. Yep.
So we're getting I and J. I and J are the parameters of swap, which we know are on the stack like that because that's how the stack handles functions.
Yes. And that standard is universal to across all compilers. Yep.
Just on a side note, if we didn't have integer, say we had a char, we would go 8, not increment by another 4, we would increment by another.
No. Even if these are char pointers, this code will remain the same because the pointers are still 32-bit wide. Even though what they point to is only 8-bit wide, the pointers are still 32-bit wide. So the calculation is still valid here. Even if they are pointed to structures, it will still be the same because your structure can be a few hundred bytes big, but the pointer is still only 32-bit wide. Okay, so here comes the next trick. The next one is how do we exchange the values of what EAX points to with whatever EDX points to. Okay? Let's take a look at what this is going to do. I push whatever EAX points to on the stack. I push whatever EDX points to also on the stack. Then I pop, but in a wrong, quote unquote wrong order. How's that? So I'm pushing whatever PX points to on the stack, then I push whatever PY points to on the stack. But when I pop it in quote unquote the wrong order. Because the way it looks right now, if you just look at the middle two instructions, let me just highlight which two we are talking about. If you just look at these two instructions, the push L and the pop L, that's doing something like exchange already, but it's only 1/2 of the exchange. Because this is the same thing, okay, the battery is almost running out, but we are almost running out of time. So this is actually copying whatever EDX points to whatever EAX points to using two instructions. Does that make any sense? Because whatever you push is the same thing that you pop, but I changed the location of where I want to put that. Is that okay? What about the first thing that we push on the stack? Well, it's being popped by the second pop instruction. So whatever I push here is popped by this instruction. So these 4 instructions effectively is doing the same thing as exchange. It's just that I use the stack for that purpose. It's a trick, but it does accomplish the same thing. So from the perspective of teaching or instructional purposes, this is actually useful because we are just using the old instructions, push, pop, and stuff like that to accomplish something that is that they're not really quote unquote intended to do. Are we still doing okay so far with this code? Okay, we got about 3 minutes left, so we have just enough time to see, well, does it work? Right? So I'm not gonna, I won't have enough time to really track down each instruction. You can do that on your own, because this program is fairly small. You can just kind of copy and paste, using YouTube. So we'll go ahead and save both programs, recompile the whole thing, go into GDB, go to swap, put a breakpoint in main, okay, because I have this unreasonable faith in my own code, thinking that it's gonna work. So we'll run the program, print out what is I, what is J prior to the swap. And just to make sure that we are not using the C code again, because that would be cheating, I single step one time just to make sure that we get into the assembly code. Okay? Do a continue, so we get back into main, and say print what is I and what is J. They got exchanged. In other words, the code does work. Okay? So if you look at the code, you go like, well, I'm not really quite sure how or why it works the way it's supposed to, then it is a good time to go into GDB, single step the entire thing. Okay? And then you look at the content of EAX, the content of EDX. What are they pointing to? Are they pointing to the right thing at each stage of the program? Then you can actually see, oh, so that's how it works. Okay? So this is a fairly useful program for that purpose, for illustrating the concept in this class, in this specific class today, but also kind of revisiting concepts that we have already touched on in previous classes. All right, so any questions? Any questions? All right. Rosemont.
Are you still recording?
The recorder is still going. Manually turn off.
Yeah. While